Settle into whatever position you are going to sleep in. There is nothing to do here but listen, and eventually not even that. Let your eyes close. Take one slow breath in, and let it go without managing it. And another, a little slower. Now let your attention rest at the top of your head. Let the scalp soften. Let the forehead be smooth, and the small muscles around the eyes let go. Unclench your jaw, let the teeth come apart, and the tongue rest low in the mouth. Let the throat be soft, and the back of the neck long. Let your shoulders drop away from your ears. Feel the weight of your upper arms, then your elbows, then your forearms. Let your hands lie open or curled however they want to be. Let the fingers go. Let the chest be easy. You are not steering the breath now. Soften the belly. Let it rise and fall on its own. Let the whole length of the back give its weight to what is underneath it. Let the hips be heavy, and the small of the back release. Feel your thighs grow heavy, and then your knees. Let the calves soften, and the ankles. And let your feet go, all the way to the toes. Now feel the whole body at once, heavy, warm, held. There is nothing left to hold up. From here on there is only a voice, and a story about a color. You do not have to follow it, you do not have to remember any of it. Let it carry you down. The color that had to be invented. Egyptian blue, the near infrared, and the last color still detectable on an ancient painted surface. A room in the British Museum has to be dark for the work about to be done in it. Not dim, but dark, with the windows blocked and the overhead lights off, and the small green standby lamps on the equipment taped over. Because the signal being looked for is faint enough that stray infrared from an ordinary lamp will swamp it entirely. In the middle of that darkness stands a marble figure from the Parthenon, carried out of Athens by Lord Elgin and bought by the British government in 1816. It is white, in the way everybody expects classical sculpture to be white. Part of the reason it is quite so white is that in the late 1930s workmen went over the Parthenon sculptures in London with copper scrapers and an abrasive to brighten them. A cleaning pushed for by Lord Duveen, who had paid for the gallery that housed the collection. A conservator switches on an array of red lamps, light-emitting diodes, chosen because they put out a narrow band of red and almost nothing else. Under them the marble turns red, as any white thing would. Then a camera opens its shutter for 5 seconds. It is an ordinary commercial camera, with 2 changes made to it. A small filter that normally sits over the sensor to block infrared has been taken out, so the chip can register light out to about 1100 nanometers. Human vision runs from roughly 400 nanometers at the violet end to about 700 at the red end. So the camera can now see a long way past where a person stops. Over the lens sits a piece of dark glass that blocks everything shorter than about 830 nanometers, and that means it blocks all of the red light in the room. This arrangement works because of a gap. Egyptian blue, a blue pigment first made in Egypt about 5,000 years ago, absorbs red light at around 630 nanometers and gives out light of its own at about 910, out in the infrared where nobody can see it. Nearly 300 nanometers separate what it takes in from what it returns. Wide enough that a single piece of filter glass can block one completely and pass the other completely. Through that glass, in that light, the marble should look like nothing. On the screen there is a black rectangle with points of white in it, specks and lines of specks, and in places whole shapes. A curl, a repeating band, the outline of a leg bent as if running. Paint making those points is about 2,500 years old, and it is the only color on that marble this technique can see. Chemically, the compound is calcium copper silicate. Its mineral name is cuprorivate, and as a pigment, it has been called Egyptian blue for as long as anyone has been able to identify it. It is generally described as the first synthetic pigment in human history, and a recent review of the archaeological evidence places its emergence at around 3,100 years before the Common Era, right at the point where Egypt becomes a single kingdom. What it does, and what almost no other material available to the ancient world does, is emit light in the near-infrared when visible light falls on it. Point red light at Egyptian blue, and it radiates back at 910 nanometers, invisibly, steadily, for as long as the red light is on. It does this under a layer of varnish, and when the grains are too few and too small to see, and when the pigment has been mixed into a color that was never blue in the first place. That behavior is called visible-induced luminescence, and the paper that established how to photograph it was written by Giovanni Verri, a conservation scientist then at the British Museum, and published in 2009. Luminescence itself had been known. What made it practical was smaller, use light-emitting diodes. Ordinary tungsten lamps and camera flashes spray infrared along with everything else. Diodes emit almost none of it. Set up correctly, the whole procedure is a photograph. It takes a few seconds, it costs nothing per image, and it never touches the object. A conservator can walk a camera along a carved band of stone and come back with a map of the Egyptian blue on it, down to individual particles smaller than a millimeter. In October 2023, Verri, by then at the Art Institute of Chicago, and a team including British Museum conservators published a paper in the archaeological journal Antiquity called The Goddess New Clothes, the carving and polychromy of the Parthenon sculptures. Polychromy is the term for the many-colored painting that ancient sculpture and architecture originally carried. One of the paper's authors, Ian Jenkins, had died 3 years earlier, having co-written the previous scientific study of paint on the same marbles 35 years before. Another was a historian of textiles, and that expertise is why the patterns they found could be read as clothing. They found Egyptian blue, together with gypsum white and probably bone white, on 11 of the sculptures from the pediments, the triangular gables at each end of the temple, and on one figure from the frieze, the carved band that ran around the building inside the columns. On the figure of Helios, the sun, rising at the corner of the east pediment, blue sits in the area of water he rises out of. Wavelets, painted in the same way that vase painters of the period indicated water. On the figure of Dione, a goddess seated further along the same pediment, there are patterns on the carved cloth. A battlement border along the edge of a mantle. A palmette, a fan of stylized leaves, tucked into the protected recess under her knee where the weather could not reach. And on the garment itself, the outline of bent human legs, as if running to the right. A sculptor carved that drapery. A painter then put a scene onto the carved drapery, figures in motion of the kind found on vases of the same decades, so that the goddess wears a cloth that has a picture on it. That carving is already extraordinarily elaborate, and the paint added a second order of elaboration on top of the carving, at a scale and a height where hardly anyone could have made the figures out. No evidence turned up that the surfaces had been roughened to help paint stick. Even so, the paper concludes, carving and color were unified in their conception. One colored pigment besides the blue was found on the figure of Aphrodite. A purple, tentatively identified as containing an anthraquinone, the class of dye molecule found in madder root and in certain insects. X-ray fluorescence, a technique that reads which chemical elements are present by the characteristic X-rays they give off, found no bromamine in it, and purple from shellfish carries bromamine. A plant or an insect is the likely source. Very and his co-authors describe what they found as a wealth of surviving paint, and arguably, they say, the best preserved polychromy of mid-5th century Athens, 4.5 centuries before the Common Era. It amounts to blue, 2 whites and 1 purple, that last on a single figure. In the same paper, they say the evidence, though greatly expanded, is still insufficient to reconstruct such a large and complex work of art. Very put it to a reporter that these are just thin paint layers at the very, very top of the surface. That interpretation of such small traces is always complicated, and that it is also possible some traces were inadvertently removed during past conservation treatments. Chemists of the 19th century had already found this material and written it down. In 1809, Jean-Antoine Chaptal, a French chemist and industrialist, analyzed the pigment pots excavated at Pompeii and reported a blue among them. In 1815, Humphrey Davy published on the colors used in painting by the ancients, having found lumps of deep blue frit in the rubble of the baths of Tyrus in Rome. Frit is the word for a mixture of minerals fused at high heat into a glassy solid and then ground up. And in 1837, Michael Faraday received 6 samples of coating scraped from temples in Athens and wrote back on the 21st of April with an analysis. 2 of them were a frit colored by copper, with wax present. 3 others were colored by a carbonate of copper, again mixed with wax. A frit colored by copper is precisely what Egyptian blue is. Ancient polychromy was known to the 19th century then. It was argued about at length and with heat. What the century did not have was any way to find paint that had stopped being visible. So the debate was conducted over a shrinking population of traces a person could still see. To make the pigment, an ancient workshop needed 4 things: a source of silica, meaning sand, a source of calcium, meaning lime or limestone, a source of copper, either copper metal filings or the green and blue copper minerals malachite and azurite, and heat. Usually there was a 5th thing, a flux, to lower the temperature at which the reaction will go. The flux was either natron, a naturally occurring soda salt collected from dried lake beds in Egypt, or the ash of salt-tolerant plants. Temperature is the difficulty. Below about 850 degrees Celsius, cuprorivate does not form. Above about 1050 to 1100 degrees, it comes apart again. The window is roughly 200 degrees wide, in a wood-fired furnace, with no thermometer. Experimental reconstructions suggest the firing had to be held inside it for somewhere between 10 and 100 hours. Somebody worked this out. Theophrastus, a Greek writing in the 4th century before the Common Era, says in his treatise on stones that the Egyptian variety of kyanos, his word for the deep blue, is manufactured, and that those who write the history of the kings of Egypt state which king it was who first made fused kyanos in imitation of the natural kind. Theophrastus does not pass on the king's name. He also notes that kyanos makes 4 colors depending on how it is prepared. That is the earliest surviving statement of something anyone who has ground the pigment discovers. Egyptian blue gets paler the finer you grind it, because smaller crystals scatter more light back out. Only one recipe survives, and it is in Latin, in the 7th book of Vitruvius's On Architecture, a Roman technical manual for builders written around 3,000 years after the Egyptians started making the stuff. Blue, he says, was first manufactured at Alexandria, and afterwards by a man named Vestorius at the town of Puteoli on the Bay of Naples. Sand is ground together with powdered natron until the mixture is as fine as meal. Coarse filings of Cyprian copper are added. The paste is rolled into balls by hand and dried, and those balls go into an earthen vessel in a furnace, where the copper and the sand, heating together by the intensity of the fire, impart to each other their different qualities and thereby acquire their blue color. Sand natron copper. No calcium appears in that list. Without calcium, there is no cuprorovate, and the whole thing fails. Whether the calcium is hiding somewhere else in Vitruvius's vocabulary, under a term whose meaning has drifted, is a live question among specialists. That recipe is incomplete in a second way, which took until 2025 to establish. A group at Washington State University and the Smithsonian's Museum Conservation Institute made 12 different versions of Egyptian blue, varying the copper source, varying whether flux was present, and varying the firing time from 1 hour up to 11 hours, all at 1,000 degrees, far shorter runs than the ancient ones. They compared the results against 2 genuine ancient specimens. Identical material, fired identically, came out substantially different depending on whether it was pulled out to cool in the air or left to go cold slowly in the furnace. Slowly cooled material had around 70% more cuprorovate in it, less of the glassy, non-crystalline material that dilutes the color, and a visibly bluer look. No ancient source records how long to leave the kiln alone afterwards. Pliny the Elder, a century after Vitruvius, gives the market instead of the method. In his Encyclopedia of the Natural World, he lists the kinds of blue, Egyptian and Scythian and Cyprian, the Egyptian most esteemed, and then the prices. 8 denarii a pound for the ordinary grade, 11 for the Vestorian, and the washed pale grade at 10 denarii a pound, above the price of the ordinary blue, because washing and settling out the finest particles is labor. At the bottom of the same market sits a poor version of the pale grade selling for about 1/30th of what the good pale grade costs. Manufacturing sites are known, and they are industrial. Amarna in the 14th century, before the Common Era, with evidence of both making the material and working it. Memphis, in the flat country south of modern Cairo, running from the 3rd century before the Common Era into the 2nd century after it. In the late Bronze Age, the product moved as flat cakes, 15 to 20 centimeters across. By the Hellenistic and Roman period, it moves as pellets 1 to 4 centimeters across. Cuprorovate is a layered silicate. Sheets of silicon and oxygen, built out of 4-membered rings, stacked with calcium and copper between them. Each copper atom sits in a flat square of 4 oxygens, an arrangement called square planar coordination, unusual and very symmetric. That geometry sets the energy levels of the copper's outermost electrons, and those levels in turn determine which wavelengths of light the crystal will absorb. It absorbs strongly in the red and orange, and again further into the green. What it does not absorb, it reflects. Having absorbed a red photon, the crystal has to put the energy somewhere. Most materials shed it as heat almost immediately. Cuprorovate instead drops back down and emits a photon of its own, at 910 nanometers. Longer wavelength means lower energy, so the light that comes out is weaker than the light that went in, and the difference has gone into the crystal as a small amount of warmth. Whatever produces that photon is what physicists call a forbidden transition. Forbidden here does not mean impossible. It means the symmetry of that square of oxygens makes the step very improbable, so it happens slowly. The copper ion stays excited for about 107 microseconds, a very long time to hang around for this kind of process. Normally, that would be fatal to the brightness, because an excited state that lingers has time to lose its energy through vibration, shaking it out into the surrounding crystal as heat. Egyptian blue is not dim. About 1/10 of the photons it absorbs come back out as infrared light, and the paper reporting that measurement, published in the journal Chemical Communications in 2009, put the pigment roughly 10 times above the near-infrared emitters then available. Why it gets away with the long lifetime is not spelled out in that paper. The usual explanation is that the crystal is rigid enough to give the energy no way out, except as light. Later work in Turin, making the compound without a flux and with very fine silica, has pushed the efficiency to around 30%. Ancient Egyptian blue falls short because it is not a pure substance. It is cuprorovate crystals sitting in a mixture that includes silica and glass, and the copper-rich glassy part absorbs the energy and gives back nothing. A study published in 2020 went further and found that 2 grains of essentially the same elemental composition can differ in whether they glow, depending on how the silicate network is linked together. For a long time, the assumption behind all of this was that Egyptian blue was used in order to be blue. Mummy portraits are the painted panels from Roman Egypt, 1st to 3rd century, set over the faces of the wrapped dead. Those best known come from the Fayum, the fertile depression west of the Nile. A consortium of museums coordinated by the Getty in Los Angeles has been running a technical survey of these panels across many collections, and one contribution to its 2020 volume by Gabrielle Thibautot reports Egyptian blue in at least 47 of them, drawn from every known production center. In those panels, the pigment sits in shaded, cool flesh tones, in gray backgrounds, and in the whites of eyes. Thibautot's summary of the pattern is that Egyptian blue is most often mixed with other pigments and rarely achieves the hue we would consider blue. A team at Northwestern University, led by Mark Walton, had found the same thing in 2015, examining panels from an Egyptian site called Tebtunis. 6 of 15 used Egyptian blue in the underdrawing and in the modulation of shading, where the finished painting shows no blue whatsoever. Walton's response was that this defies expectations for how the pigment would be used. Very has described the same habit in sculpture. A touch of Egyptian blue added to the white paint of the eyes makes them seem translucent. It keeps the white from reading as flat and gives it the faint, cool cast that a real and slightly wet eye has. In Rome and Egypt, then, a great deal of the Egyptian blue that can now be detected was put there by people who did not want it seen as blue. Egyptian blue kept being made after Rome fell. An analysis published in 2021 examined the pigment from a church above Gratsch in South Tyrol from a building phase that archaeologists date to the 5th or early 6th century. Trace minerals in it pointed to a source in the volcanic country around the Bay of Naples, which is Vestorius's region, the Pureale of Vitruvius's sentence. Somebody was painting an Alpine church before the middle of the 6th century, with pigment made from Campanian sand. Whether that pigment was freshly made or old stock, the paper does not say. At Castelceprio in Lombardy, an early medieval church holds a cycle of wall paintings, and the Egyptian blue in them is odd. It is rich in zinc, with the zinc concentrated in the glassy material around the cuprorovate crystals rather than inside the crystals themselves. Someone making the pigment from brass would produce exactly that. Brass is copper and zinc, and no ancient recipe for Egyptian blue calls for brass. Then it turns up in the Renaissance. In 2020, a survey mapped Egyptian blue across Raphael's Triumph of Galatea at the Villa Farnesina in Rome, painted in 1512. 5 years later, in 2025, a systematic survey of Italian paintings in the Louvre, storerooms included, found it in a picture painted between 1503 and 1505 by Perugino, who had been Raphael's teacher, and in a nativity altarpiece of about 1506. Also in 2025, 3 independent techniques identified it in Raphael's Christ Blessing, a panel of 1505 to 1506, in the sky and parts of the landscape, where the authors concluded it was a deliberate choice rather than a cheap way of stretching ultramarine, the ruinously expensive blue ground from imported lapis lazuli. Perugino's use of the pigment precedes the Galatea by about 9 years. A proposal from the Louvre team is that it passed from master to pupil inside a single workshop tradition in central Italy, a guarded workshop secret. They put the remaining question in the paper without settling it. Was this the result of reusing ancient artifacts or of remnants of historical production techniques? Antonio Sgamelotti, a chemist who has worked extensively on Raphael's frescoes, has pointed out that Raphael wrote to a friend that he had received great help from Vitruvius while working on the Galatea, which would mean a reconstruction from the ancient text. A conservation scientist, Jorn Bredel Jorgensen, has offered a different account, that the production technology survived locally all along, and that the gap in the historical record will keep shrinking as more paintings are examined. Laboratory work on the compound goes back to a French geologist in 1889. Conditions for making it were pinned down in 1914, when a paint chemist and two colleagues published a paper simply called Egyptian Blue and reproduced the material. From chaptals, pigment pots to that laboratory took a full century. A year later, a writer on color assessed the commercial prospects. Interest attached to the subject of Egyptian blue, he wrote, is rather academic than practical, for this pigment is not now made except on a small laboratory scale. Infrared emission turned out to solve problems that had nothing to do with archaeology. Conventional fingerprint dusting powders work by contrast or by glowing under ultraviolet light, competing with whatever colors and patterns and reflections are already on the surface. Drink cans, holographic polymer banknotes, or printed packaging. Finely milled Egyptian blue works as a fingerprint dusting powder. In the near-infrared, at 910 nanometers, the busiest surface in the world is silent. A printed drink can is uniformly black there. It outperformed the commercial products on exactly the patterned and reflective surfaces where the commercial products fail. Stir it in water at about 85 degrees for a fortnight, and it comes apart into sheets roughly a nanometer thick, which is a single layer of the crystal. A discovery made at the University of Georgia in 2013. A forensic version stirs for 11 days, producing flakes under 5 nanometers thick, and coats them with a compound that makes them cling to oil. So the powder sticks to the greasy residue of a finger mark rather than to the object underneath. It works on prints 2 weeks old, and it was tested on Australian $5 polymer notes. Across the color-shifting bird and the transparent window and the portrait, all of which defeat ordinary powders. Photographing the result takes the same modification as the rig in the dark room at the museum. Infrared blocker out, dark glass on the lens. Looking inside living tissue is the second problem. Biological material scatters and absorbs visible light heavily, and it glows faintly on its own, so a great deal of microscopy is a fight against the sample. There is a window in the near-infrared where tissue is comparatively transparent, and the field working in that window is chronically short of good fluorescent labels. Quantum dots, the semiconductor nanocrystals usually reached for contain heavy metals. Organic dyes fade under illumination. Carbon nanotubes are dim. In 2020, a group led by Sebastian Kruss published on Egyptian blue flakes as a label for this window. They do not fade, they are considerably brighter than carbon nanotubes. They are not toxic, and the team used them to track single particles inside living fruit fly embryos and inside the tissues of a plant. Follow-up work found the signal still readable through 4 to 5 millimeters of tissue-like material. Instruments have collapsed in price. Modified night vision goggles identify the pigment in real time. A commercial pair costing about $100, with a $1 screw-on lid covering the built-in illuminator on one side and a $30 infrared filter on the other. No internal modification. It was tested at the Egyptian Museum in Turin, in the buried rooms of Nero's Golden House in Rome, and at the Villa Farnesina, and it detected the pigment from more than 12 meters away, in low light, with no special illumination. Its authors caution that image quality is lower than a properly optimized photographic setup, and that serious work should still be done with the established tools. The paint came off. Some of it weathered away over 2,500 years on a hilltop. Some of it was scrubbed off in the 1930s by the cleaning at the museum, and Very has said that some may have gone inadvertently during ordinary conservation since. Whiteness of the sort the 19th century took for a classical ideal was in part something the 19th and 20th centuries produced. Method came off too. No Egyptian source records how to make it. Theophrastus says that Egyptian records name the king who invented the pigment, and then does not pass the name on. That one surviving recipe in Latin, 3 millennia late, leaves out the calcium and leaves out the cooling as well. On the Parthenon sculptures, nobody has detected a shellfish purple, or a red, or a yellow, or a green. Blue was the awkward color to get hold of. Azurite turns green with time. Lapis lazuli had to be carried out of Afghanistan. So somebody made a blue instead, in a 200-degree window in a wood-fired kiln, and made it better, as we now know, by leaving the fire to go out slowly. That manufactured blue is the color still there. Put red light on it, and it answers at 910 nanometers, the way it would have answered on the day it came out of the furnace, and the way it went on answering through the scraping and the cleaning and 2 centuries of being called white.